Hello, everyone. Welcome to Unit 7 Stoichiometry, Lesson 2, Concentration and Molarity. I'd like to begin today by going over the homework problems from the stoichiometry lesson. We take a look at problem number 1. We were converting from grams into grams. Anytime we're going from grams to grams, we're looking at a 3-step problem. The first step is going to be converting grams into moles. Second step is to use our balanced equation to go from moles of one substance to moles of another. And our third step is to take that moles of the new substance and convert it back to grams. So in this case, we were going from oxygen. We convert that into moles by dividing by the molar mass of oxygen. In the next step, we convert from moles of oxygen to moles of hydrogen. In this case, using the coefficients from the balanced equation. You don't always have to go from reactants to products. You can go from one reactant to another reactant like we're doing here. In our last step, we're going to convert from moles of hydrogen to grams of hydrogen, again using the molar mass from the periodic table. We wind up with a mass of hydrogen in grams. In example number 5, we're going from moles to grams. So this is only a 2-step problem. If you remember, according to our map, we have mass of A, moles of A, we have moles of B, and mass of B. In problem number 4, we went all the way from mass of A to mass of B, which is why it was a 3-step problem. In problem number 5, we're going from moles, so we're actually starting here, and we're finishing with mass of B, so our mass of liquid water. So this is a 2-step problem. So I only need to set up 2 fractions here. So we start off with moles. Now, our first step is this conversion here from moles of A to moles of B. This is where we use the coefficients from our balanced equation. So in this case, we start off with 5 moles of lead-2 hydroxide. We convert that immediately from moles to moles of water. And then we convert moles of water back to grams of water. And we wind up with our grams of water. Keep in mind, the number of significant figures is largely going to be based on what number you're starting with. So if you're given 3 significant figures at the start, that's going to limit your answer to 3 significant figures. Question number 6 says convert 15 grams of calcium bromide to moles of calcium sulfate. So in this problem, let's get rid of these. In this problem, we're starting off with mass, but we're finishing with moles. So again, it's a 2-step problem, but this time the conversion from moles to moles is our second step. So we're going to begin with grams. We're going to convert from grams to moles of calcium bromide. Moles of calcium bromide to moles of calcium sulfate, and we're going to finish with moles of calcium sulfate. We take a look at numbers 7, 8, and 9. Again, here we have a 2-step problem from grams to moles. So we go from grams of methane to moles of methane to moles of carbon dioxide. And again, these parts that I have shaded in blue, those are the ones that are coming from the coefficients in the balanced equation. In question number 8, notice that we're starting in moles and we're finishing in moles. So this is a 1-step problem. The only step that I need in this problem is that mole to mole conversion using the coefficients from the balanced equation. In question number 9, we have another gram to gram problem. So grams to grams are 3-step problems. So we start off in grams, we go to moles, we convert from moles of, in this case, octane to moles of oxygen. And then finally, from moles of oxygen back to grams of oxygen. In problems 10, 11, and 12, we have a mole to gram problem. So that's going to be a 2-step. Our first conversion will be our mole to mole conversion. In question number 11, we have a gram to gram problem. That's our 3-step problem here. In question number 12, we have a gram to gram problem. So that's another 3-step problem here. Notice that when you're going between grams and moles, we always use 1 mole, just like we did back in October and November. So anytime I'm going from grams to moles, I'm using 1 mole, regardless of what the numbers say up here. The only time that we use these coefficients is when we're changing what substance we're talking about, when we're going from moles to moles. Other than that, grams to moles, we use 1 mole. Moles to grams, we use 1 mole. And finally, with our last problem, we have convert from moles to grams, so a 2-step problem. We start off, because we're starting off in moles, we start off with our mole to mole conversion. We convert that to grams to get our final answer. Again, if you still have questions about the stoichiometry problems, please set up a time with me or consider stopping by office hours. All right, let's get into lesson 2. So lesson 2, as it says in the title, deals with concentration and molarity. As you can see on the board behind me, it says concentration is the amount of a particular substance in a given quantity of a mixture or solution. So the first time I learned the word concentrate was reading cans of frozen orange juice when I was a kid. Now, concentration can have multiple units. So we could talk about concentration in terms of percent, in terms of molarity, like we'll use here, molality. There are tons of different ways to express the concentration of a solution. However, molarity is what we're going to use most often. In the case behind me, if we look at the definition for molarity, it is the concentration unit expressed as moles of solute per liter of solution. Now, we often confuse the terms solvent and solution as being the same thing, but the picture here will illustrate that they're actually 2 different things. So first, if we talk about solute, that is the substance that is being dissolved. So in this picture, it looks like we have some copper 2 sulfate here, and we're dissolving it in water. The copper 2 sulfate, the substance that's being dissolved, is our solute. The substance that is doing the dissolving is called the solvent. The solvent is the water by itself. The combination of the 2 of them we refer to as our solution. So back when we were doing chemical reactions, we were using the term aqueous. Aqueous was the term that we used for a solution of a solute dissolved in a solvent. That combination is what we were talking about when we use the term aqueous solution. That's the mixture of both of those together. If we look at this part of the map once more, you're going to see that what we're doing is introducing kind of another branch here to our map, the relationship between volume and moles. Just like we saw the relationship between grams and moles, here we used our molar mass from the periodic table. Same thing over here. We used our molar mass from the periodic table. For this part, we used our balanced equation. So for this part in green that I'm shading, when we went from moles to moles, we used the coefficients from the balanced equation. Now we're introducing this other starting point. So when going between volume and moles down here, we're going to use concentration. And we're going to do that in moles per liter or molarity. These 2 mean the same thing. They're just 2 different ways to express the same thing. Same thing over here, either moles per liter or molarity. Okay, let's take a look at some examples. So in our first example, you can see that we have sodium carbonate. So sodium carbonate, as a remember, is Na2CO3. It's added to enough water to bring the total volume of the solution. So the solution has a volume of 250 milliliters. So the actual amount of water is probably a little less than 250 milliliters because it's the combination of sodium carbonate and water together that has a volume of 250 milliliters. It's important to note that difference because the volume of the solvent is not necessarily equal to, in fact, is not equal to the volume of the solution as a whole. Okay, let's take a look at this problem. So we're going to start off here with 175.32 grams of Na2CO3. Remember, if we are looking to figure out the concentration, we're trying to identify the number of moles per liter. So if we have grams, our first objective is going to be to convert that number of grams into moles. To do this, what we're going to need to do is find out the molar mass of sodium carbonate. So if we look up sodium on the periodic table, sodium is equal to 22.99 grams per mole. In this case, we have to multiply that by 2 because we have a subscript of 2. We have carbon. Carbon has a molar mass of 12.01 grams per mole. And we have oxygen. That has a mass of 16 grams per mole. We'd have to multiply that by 3. We wind up getting a molar mass for sodium carbonate equal to 105.99 grams per mole. Now, we have units of grams on top. That means in our ratio, we want to put the 105.99 grams of sodium carbonate on the bottom. So that unit will cross out here. And on top, we're going to put 1 mole of sodium carbonate. Okay, on the next fraction, we are trying to end up with an answer in moles per liter. So we need to put liters on the bottom. We have a volume right here, but that volume is in milliliters. So what you have to do in order to convert from liters or 2 liters from milliliters is to move your decimal place 3 spots. To 1, 2, 3 spots to the left. We wind up getting a volume when we convert it to liters that is 0.2500 liters of solution. We have a 1 on top. That's just because we're dividing by this number. So now we can type this part into our calculator. So we're going to have 175.32. We're not going to do anything with a 1 on top. Again, multiplying by 1 and dividing by 1 has no effect on your answer. So don't even bother typing it into the calculator. So 175.32, forget the 1. So I'm going to hit divided by 105.99. And then once again, divided by 0.2500. So I wind up with this answer. Now, same rules as before in terms of significant figures. I have 5 here, 5 here, 4 significant figures here. So my answer is going to be limited to 4 significant figures. So if I drag that answer out here, I have 1, 2, 3, 4. This is the 4th significant figure here. I look behind it, it's only a 4. So I'm going to leave it as 6.616. Notice that my units, moles per liter, Na2CO3. Or if I choose, I can also report my answer as 6.616 molar Na2CO3. Both of these are correct answers. Remember that capital M is one way to express molarity, moles per liter is another. Okay, I switched over to my computer so I can show you exactly how I would like you to type these in as we go over them. So in our first problem, we have a molarity problem. This problem is going to be almost identical to the problem that we just covered. So we're going to start off by figuring out the molar mass for sodium chloride. So if we look up sodium on the periodic table, we'll find out that it has a molar mass of 22.99 grams per mole. Chloride has a molar mass of 35.45 grams per mole. And if we add those together, we'll get a total mass for NaCl that is equal to 58.44 grams per mole. Now, we're going to begin with the 50.1 grams of NaCl. we're going to need two different fractions in our problem, just like in our example problem, in order to convert into moles per liter. So I'm going to set up my two ratios first. Now, if I go back and look at my molar mass is 58.44 grams. Now, in order for the unit of grams to cross out, I need to put that 58.44 grams of NaCl on the bottom. And on top, I'm going to put in my 1 mole of NaCl. In my second fraction, remember that I want to end up with moles per liter. If we take care of crossing out units right now, you'll notice that right now, once my grams of NaCl cross out, right now I have units of moles of NaCl on top, which is great, but I need to get moles per liter. So on the bottom here of this fraction, I'm going to type in my volume of 0.2500 liters of solution. And now using my calculator, bring up my calculator so that everyone can see it here. Using my calculator, I'm going to type in 50.1 divided by 58.44 divided by, because it's on the bottom, divided by 0.2500, and I wind up with this as my answer. Now, I'm going to copy this part down, and then we'll talk about how much of this we want to keep. So I'm going to just copy a whole bunch of this. We're not going to keep all of it. Instead, if you notice, we're limited to just 3 significant figures because of the 50.1. So when I look at this problem and I keep it to just 3 significant figures, I have 3.429. So the 2 is going to be my last significant figure. I look behind it, it's a 9. So I'm going to wind up with a final answer of 3.43, either moles per liter or capital M, molar NaCl. I'm just going to highlight that as my final answer. Okay, in our second section, we're actually going to work backwards. So in this section, we're given a solution volume of 500 milliliters. We're given a concentration of 0.5 molar cupric nitrate, and we're actually trying to figure out how much solid would have to be weighed out in grams in order to prepare this solution. So my suggestion to you when you do these problems is to begin by figuring out the molar mass of cupric nitrate in this problem, or whatever the substance that's being dissolved is. So if we write out the formula for cupric nitrate, we have CuNO3 2. So copper is equal to 63.55 grams per mole. We have nitrogen, which is equal to 14.01 grams per mole, but we need to multiply that by 2 because of the parentheses and the subscript of 2 outside the parentheses. And then for oxygen, which is 16.00 grams per mole, we're going to need to multiply that by 6 because we have 6 oxygens in our total. So I'm going to add these all up, and we're going to get the molar mass for CuNO3 2. Bring up our calculator here. So we have 63.55, that's for copper, plus 28.02, that's for 2 nitrogens, plus 96, that's for my 6 oxygens. So I wind up with a molar mass of 187.57. Now I can begin to set up my problem. When you're setting up these problems, we're actually going to start with our volume. So we're going to begin, if you think about the map that we saw when we were going over our notes, volume is a starting point, just like mass was a starting point. So in this case, we're going to start off with our volume of 500 milliliters. But instead of putting down 500 milliliters, I'm going to divide that by 1,000. So move the decimal place essentially 3 spots. And we'll wind up with 0.500 liters of solution. Now we're going to set up our fractions. Once again, we're going to have two fractions here. So in our first fraction, we are going to convert from liters into moles using my molarity, my concentration here. So what that concentration of 0.5 is, or means, is that we have 0.500 moles of CuNO. We're going to start by using our 0.5 molar cupric nitrate solution. So what that concentration means is we have 0.500 moles of CuNO32. Remember that that capital M can be broken down into moles per liter per 1 liter of solution. And now liters of solution here and liters of solution up here cross out. In our next fraction, we have 1 mole of CuNO32. Remember, we're trying to ultimately get to grams. So we have 1 mole of copper nitrate, and then on top, we're going to put our molar mass. This is going to represent the amount of copper nitrate that we have to weigh out in order to prepare this solution. One of the nice things about using all of these units is it kind of tells you how to approach the problem. We know that we have to wind up with an answer in grams because we're weighing out a substance. So that helps us to figure out, okay, well, grams has to end up on top in our last fraction in order for that to happen. So our moles of copper nitrate on top and bottom will cross out. The unit for that will cross out. And now let's type this into our calculator. So we start off with 0.5 for our copper 2 nitrate volume. Then we're going to multiply by 0.5. Then we're going to multiply by 187.57 in order to get the mass that we would need to weigh out in grams. So that turns out to be this number, 46.8925. So I'm going to copy that. We're going to put that in right there, but remember, we are going to figure this out based on significant figures. So in this problem, we only have 3 significant figures. So our third significant figure is right here, this 8. So 1, 2, 3. We look behind the 8, it's a 9. So that means we're going to make this a 9. We're going to get rid of all of that. And we finish off with grams of copper 2 nitrate. That's it. That represents the mass of copper 2 nitrate that you would need to weigh out in order to prepare 500 milliliters of a 0.5 molar cupric nitrate solution. Okay, in our third and final type of problem, beginning with problem number 6, we're asked to figure out the final volume that would be required in order to prepare these solutions. So what we're going to do here is we're going to start off with our moles of, in this case, lithium sulfite. We're going to convert from moles into a volume using our concentration. So this, believe it or not, is only a one-step problem. So we have 4.67 moles of Li2SO3. And we are going to begin by setting up our ratio here. Again, this is only a one-step problem. So now we need to cross out moles and end up with liters. So in order to do that, moles have to be on the bottom, liters have to be on top. Well, remember, this capital M that we have up here actually represents moles per liter. So we're going to start off on the top by saying that we have 1 liter because we need moles to cancel out. So that part needs to go on the bottom. And on the bottom here, we're going to have 4.50 moles of Li2SO3. So when you have a fraction, 4.50 moles per liter, you can write moles on top and liters on the bottom. or you can flip that fraction and write liters on top, moles on the bottom. You use whichever one will allow you to cross out units. So in this case, because we have to cross out units of moles, we need to put the mole part on the bottom. We'll flip it over and put the liter part on top. So this will be liters of solution. So now our final answer is simply 4.67 divided by 4.5. So now we get this answer here. I'm going to copy that down and paste it right here. Now, this answer is in liters. So let's first fix this for significant figures. So if you notice, here's our third significant figure, which is what our limit's going to be. We look behind it, it's a 7, so that means we're going to change this to a 4 instead of a 3. Now, the problem specifically asks for milliliters of solution. So as a reminder, our problem asks for an answer in milliliters. So we're going to set up a second step here where we convert from liters into milliliters, and you can do this in your head. But just as a reminder for everyone, the conversion between liters and milliliters, so 1 liter of solution is equal to 1,000 milliliters of solution. So 1.04 times 1,000 is 1,040 milliliters of solution. In this case, it's Li2SO3 solution. So our third type of problem, a little easier. It's only one step. We don't have to figure out a molar mass. We're simply converting from units of moles into units of liters using the concentration as our ratio. Okay, everyone, that wraps up the lesson 2 on concentration and molarity. Please finish this homework assignment. If you have questions, please stop by office hours or set up an appointment using Calendly. Hope everyone has a great week. Thanks, everyone.